Wait. Hello. Okay, there it is. I didn't think I had my sound on. Okay, Taylor's theorem and estimating remainders. Okay, and we may even talk about what happens when the radius of convergence is finite. Yes, that's a problem. So, okay, this is a Taylor series. It's related to Maclaurin. Okay, remember Maclaurin was this. All right, so there's a Maclaurin series. Okay, Maclaurin is in powers of x, and it's good for x equal to a or x near a. Let's see, how did I write this? Well, I'm sorry, I said it wrong. It's good for x equals 0 or near 0, say some radius of convergence around 0, or everywhere, right? That's Maclaurin. That's what we've been doing up to now. But what if the radius of convergence is finite? So it's good near 0. But you need it good somewhere else, like 10. You want to find f of 10. Remember, this is supposed to be a function. You're estimating f of 10 with this thing, let's say, and the radius of convergence doesn't include 10, let's say. You can shift Maclaurin around and change the interval of convergence. You can shift the center. And that's what Taylor did. Here's Taylor. This is not new. You have this. This is new. This is a Taylor series. Maclaurin is a special case. It goes like this. Now remember what happens in a function. If you had f of x and then you had f of x minus a, isn't that a shift to the right, a units? The function shifts to the right, translations, yes? All right? That's all I'm doing. I'm taking a Maclaurin and I'm shifting it a units. So it's so that its center of convergence is somewhere else, more convenient if I need it to be there. All right? So what do you get? Well, plug in k is 0. You get something to 0 is 1. C0, some constant. Plus, plug in k equals 1. Some other constant, C1, this thing to the 1. Plus, C2, plus, C3. Well, I'm running out of space here, so C3, plus, okay? Now what's good about this is the interval convergence changes. It's either good at A only, which is not very exciting, because to generate this you're going to need f of A, f prime of A, f double prime of A, all that kind of fun stuff. So I already knew f of A, that's silly. Or near A. So it's going to be A minus a certain radius and A, between. A minus a certain radius and A plus a certain radius, right? So say, for example, A is, the series is centered at like 10. And the radius of convergence is 1. I'm saying it's either good at 10 or it's good between 1 and 11, if A is 10 and R is 1, let's say. So instead of A being 0 all the time, it could be whatever you want. If you make A 0, this is Maclaurin. It's good at 0, good near 0, right? Between negative R and R. Plus. Negative R and R, right? Okay, so if R is a radius of convergence of 1 and the center is, I don't know, like 10, then I'm saying, okay, it's good between 9 and 11. All right. Or everywhere. It could still be good everywhere. We find that out using the ratio test for absolute convergence for power series. Okay, so let's take a look at such a series. Here's one. All right. Are you ready? Can I move ahead of this? That's a Taylor series. That's a Maclaurin series. Same thing, except there's no A here. Same thing as Maclaurin if you let A equal 0. Okay? I'm just shifting to the right A units. Or to the left if A is negative. Okay, so here's an example. Let's say I had this series. X minus 2 over 2. Minus x minus 2 squared over 2 times 2 squared. Okay, plus x minus 2 cubed over 3 times 2 cubed. That's a times. Okay? Minus. Alrighty. So, can you get me a general term? Part A. Let's say this is a free response question. Part A. What's the general term? Any ideas? Can you write this as sigma? All right, what do you think? Sigma what?
That's
K starts at what?
K starts at 0.
0 to infinity? What?
X minus 2 to the K.
Okay.
Over,
Well, you want K to start at 1? Because look at the powers. 3, 2, 1, 3, 2. How about we start with 1? That'll be easier. So this is good then, right? Then this is 2 to the 3, 2 to the 2, 2 to the 1. So 2 to the K. But what about the 3, the 2, and the 1? That's just K. Okay. Good. So there's your general term. Wait, we forgot one thing. What did we forget? Right. So is it negative 1 to the K? Not if you started 1. Why not? You done already? Oh my goodness.
Did he get that?
I think he got 7 and 8. Nobody else did. C, D, D, A2. I think you missed 6. So 9. I think it's a 9, but I'll check later for sure. Okay. It's a 9 before the ridiculous curve. Is this correct? Yeah, we got a ridiculous curve on this one. All right, is this right? What's wrong with it? Actually, it's wrong. Yeah, if you plug in 1, you get negative 1 to the 1 is negative to start, and then positive. That's backwards. So how do you fix it? Add 1 to this. K plus 1. Just shift it off, or K minus 1. Just shift it a little bit. Okay, so there's the general term. That was part A. Now that you got a general term, part B is what's the radius of convergence. Whatever function this is, hopefully this is some kind of function. I don't know what it is. But whatever that function is, if you graph it and you graph it, where do they match? That's the radius of convergence. Remember, it has to be near. Look at what this is. Powers of x minus what? 2. Remember, Taylor is in powers of x minus a. So a is 2. So what do we know about the interval convergence? It's only 2. It's centered at 2, so it's only 2 or near 2 or everywhere. We got to figure out which one it is. I know it's got to be at least this. All right. So how do you figure it out? It's got to be a radius of convergence about 2. It could be 2, it could be near 2, it could be everything. Well, because if we plug in 1 now, K plus 1 is 2. Negative 2 squared, negative 1 squared is positive 1. I start positive. That's just a fudge factor. You can do K minus 1 if you want. Big deal. Right? Or you can go crazy here and put a 0 there. You put a 0 there, keep the K. Then you have to do K plus 1 here, K plus 1 here. You've got to fudge it a little bit to get the pattern that you want. Okay? But I think this is probably the simplest way to write it. Okay, so let's invoke the ratio test for absolute convergence of power series. And what does that say? It says let rho be the limit as K goes crazy of the absolute value of u sub K plus 1 over u sub K. Now, if this is u sub K, how do you write u sub K plus 1? X minus 2 to the K plus 1 over K plus 1 over K plus 1. All right. And then we're going to divide by u sub K. But this is u sub K. So how do you divide by this? Reciprocal. So just write this. And what happened to the negative? This is the ratio test for power series, which we did last time. What happened to the negative one? Well, it's absolute value, so it goes away. Who cares? Now we're going to force the issue. We're going to solve for all x values such that this limit is. What's good about ratio tests? Rho tests are good or show convergence when? When rho is less than 1. So we're going to force the issue. We're going to make this less than 1. We're going to find the x values that make this less than 1. Those are the x values that work in this statement. Okay? Those are the x values that make this statement true. All right? That's what we're looking for. All right? It may not be every single x value in the world. It may only be x equals 2. That's sort of a problem, but there you go. All right, so let's simplify this mess. X minus 2 to the k into x minus 2 to the k plus 1 is just... what? Careful. Yeah. Oh, you're over here. Yeah, okay. What is, how do you divide two powers of the same base? You subtract the exponents. So what do you get? K plus 1 minus k is 1. So it's just x minus 2 to the 1. Okay. What about 2 to the k over 2 to the k plus 1? Same thing, powers. It leaves a 2 in the denominator, right? And then this doesn't reduce. K over k plus 1. All right, so now this is a limit in k. We've got to do this limit. The examples we've seen up to now, the k's disappeared, and then we had an infinite radius of convergence. Here the k's don't disappear, so we'll have a finite interval of convergence. Okay. What's the limit as k gets huge of k over k plus 1? This is a constant, remember. I'm plugging in a certain value of x to see if the function works, right? This is the variable. K is going wild, so? No. Top heavy, bottom heavy, equal degree. Equal degree, so leading coefficients. It's 1. Or do L'Hopital. Derivative of the top is 1, derivative of the bottom is 1, right? So there's the limit. And that's your interval convergence. Because what does that mean? It means that x minus 2 over 2 is between 1 and negative 1. That's what that means. I remember when we had geometric convergence once, and we had something like this, and that meant numbers between negative 1 and 1, because you can plug in negative a half, you can plug in positive 3/4, you can plug in negative 5/6, and it works. Same idea. If the absolute value is less than 1, then the argument is between 1 and negative 1. Okay. So solve for x. Can you get x alone? Can you simplify that? Say this was an equation. What would you get rid of first? Which 2? The bottom. So what do? Multiply. Okay. So you got negative 2 is less than x minus 2 is less than positive 2. Multiplying everybody by 2. Then how do you get rid of this guy? Add it. So 0 and 4. So were we correct? It's either good at 2 or near 2 or everywhere. Which one? Near 2. In other words, the center of this interval of convergence is 2. Right? Isn't that what we said? What's the radius of convergence? How wide is it from 2? It's 2. All right. So this is the case that we have. A is 2 and R is 2. 2 minus 2 is 0. 2 plus 2 is 4. That's what we got. Okay. But wait, now it gets tricky. You thought it was tricky already, huh? Now it gets tricky because the endpoints you have to test separately. The power series, wait, what am I saying? The ratio test for power series for absolute convergence only tells you the size of the interval and the center of the interval. It doesn't tell you if the endpoints work too. So you have to test them separately. And that's why we spent 2 weeks on power series of constants. Because what you're going to do is you're going to plug in 0 up here and see if you get a series that converges or not. And you can tell whether it converges or not using integral test, ratio test, comparison test, or some other test. Okay? All right, so we're going to plug in 0 and see if it's good. And we're going to plug in 4 and see if it's good. All righty. So are you done with this page? Can I move to the next page? All right, so this is what we're going to do. We're going to take the series that we had, x minus 2 over 2 minus x minus 2. Well, actually, I don't have to write it that way. Let me write it the general term. What did we have for the general term? We had sigma. K started at 1, right? Then it was negative 1 to the k plus 1. And it was x minus 2 to the k over 2 to the k, right? All right. What if I plug in, that's supposedly f of x. What if I plug in 0? What do I get? Plug in 0. 0 minus 2? Okay, so you got negative 2 to the k, and you got negative 1 to the k plus 1 over stuff. Okay, so does it converge? Well, I don't know. Let's see. This starts positive, then it's negative, then it's positive, then it's negative, right? This one starts what? Negative, doesn't it? So when this is negative, this is positive. When this is positive, this is negative. So this product is always negative, isn't it? Right? So it's really just this. Yeah, that's right. Okay. All right. So what? So let's see. With a negative in front, right? Negative in front. So, do you know this series? Don't you recognize this series? What happens to these guys? They cancel. And it's the harmonic. Well, it's the opposite of the harmonic. Oh no, it starts at 1. So it's the opposite of an harmonic. But harmonics do what? Diverge. You can prove that by ratio tests. You can prove that by integral tests. We did. This is a P series where P equals 1 diverged with the P integral, with the integral test, right? Didn't we do this one? So this one diverges. So the question is this. Is 0 part of the interval of convergence? Can I put an equal sign here? Sometimes I can, sometimes I can't. So was 0 good? No, it wasn't. Okay, now let's try 4. All right, so it doesn't work for 0, so let's try it for 4. Now if you plug in 4, what do you get? Let's see, 4 minus 2 is 2. All right, so now you get, well, let me just do it here. I'm going to just plug in 4. So case 2, I guess you could think of it as 2 minus 2 is just 2 to the k, so you got 2 to the k times negative 1 to the k plus 1 over k times 2 to the k. Now, is that good or bad? It could be good at 0 and at 4. It could be bad at 0 and at 4. It could be good at 0 and not at 4. It could be bad at 0 and good at 4. I don't know. I already know it's bad at 0, right? What about 4? Is it good or bad? What happens with this? Who's that? You know this creature too. An alternating harmonic. Remember the alternating harmonic, if we start at 0, added up to ln of 2, I think we figured out, right? So it did converge. This is a little bit off. It's missing the first term, and it's starting, well, it's starting positive, that's okay, but it's missing the first term, so it's not ln2, but it converges to something, right? So this is true. So guess what? I'm going to amend my interval convergence. How do I amend it? Put a little equal sign right here. Ta-da! That's it. Whatever the heck this function is, I don't know what it is, but that's the interval convergence. Now this is a sort of silly question because usually they don't give you the series, they give you the function. And then you have to figure out the series, and then you have to figure all of this stuff out. So you would know the function, usually. Okay? So usually you start here, and then you do Maclaurin's series or whatever it is to get what you need to get. Alrighty. So how do you generate a Taylor series on your own? Well, let's see. Let me give you a function. And instead of centering it at 0, let me center it at, I don't know, 1. Okay? So can you get me a Taylor series for f of x's ln of x? Okay? At x equals 1. Near x equals 1. It's either good at 1 or near 1 or everywhere, right? But now I have to tell you Taylor's theorem. Remember Maclaurin's theorem? Maclaurin's theorem was f of x equals f of 0 plus f prime of 0 times x plus f double prime of 0 times x squared over 2 factorial plus f triple prime at 0 times x cubed over 3 factorial and so forth, right? Well, this is Taylor. F of x centered at a is f of 0. Sorry, I said it wrong. I'm saying it wrong. F of a, right? Remember, before it was the center of convergence was 0, right? Now the center of convergence is a. That's the same idea. Plus f prime at a times x minus a plus f double prime at a times, what do you think? X minus a squared over 2 factorial plus, what's the next one? F triple prime at a times x minus a cubed over 3 factorial. All right, it's almost the same. If you plug in a is 0, it is the same. All right, so Maclaurin is a special case of Taylor. Taylor is a more powerful theorem. And Taylor, we're going to talk about Taylor's remainder theorem. We're going to talk about what the error is when we truncate Taylor's series, which are infinitely long, to Taylor polynomials, which are just, say, a third degree polynomial. This would be a third degree polynomial. This is known as a third degree Taylor polynomial. This is known as a third degree Maclaurin polynomial, because it's finite. It's not an infinite series, it's a finite series. But we're usually dealing with the infinite series, so let's talk about that. Okay? All right, so let's use this theorem now to generate a power series for ln of x. Alrighty. So if f of x is ln, what's f prime? Because I need f prime at a, f double prime at a, f triple prime at a, right? So what's the derivative of ln x? 1 over x, don't forget that's x to the negative 1, right? Why do I do that? Because f double prime is easier that way. Differentiate this and you get negative x to the negative 2, also known as this. This is easier to plug into. This is easier to differentiate, right? What's f triple prime? 2x to the negative 3, so 2 over x cubed. And let's see, how many do I want? I'm going to do 5 of these. Or, do I need 5? One more. All right, so 4. So anyway, this is what? This is 2x to the negative 3, so what's the next one? It's going to be negative 6x to the negative 4, so negative 6x to the 4th. And if I need another one, I'll come back. I think that's probably enough. Now, I don't plug in 0 like I did at Maclaurin. What do I plug in? A. And I said I want A to be 1. Okay? Why can't I use 0 anyway? Because ln of 0 is undefined anyhow. That wouldn't work. So what's f of 1? ln of 1 is 0. Okay. What's f prime at 1? Well, plug in 1. What do you get? 1. That wasn't too bad. What's f double prime at 1? It's going to be negative 1 if you plug in 1 here. Okay. Give me a pen. All right. F triple prime at 1 then is 2. And f quadruple prime at 1 is negative 6 and so forth. Okay. So remember these numbers. 0, 1, negative 1, 2, 6. 2, negative 6. So it's 1, it's negative 1, it's 2, it's negative 6. And the first term drops out. All right, let's do Maclaurin. Can I move to the next page? Okay, here we go. So ln of x will be approximated by, or it's exactly equal to this if you have infinitely many terms, on its interval convergence, whatever that is, I don't know what it is yet, right? Of f prime, f of a, which was 0, plus f prime at a, which was 1, times x minus a, which is 1, minus, well, plus f double prime at a, which was negative 1, times x minus 1 squared over 2 factorial, right? So it was 1, negative 1, what the heck was it? 1, negative 1, 2, negative 6? Okay, I'm going to continue here. What's the next term then? Plus 2x minus 1 to the third over 3 factorial, right? And then the next one was plus, it was 1, negative 1, 2, and what?
Minus 6.
So minus 6, okay. Minus plus a negative, right? So minus 6, what? X minus 1 to the 4th over 4 factorial, and so forth. Okay. So can you get me a general term out of this? Well, what's 2 into 3 factorial? It's just 3. What's 6 into 4 factorial? It's just 4. So the factorials are gone. It's just 4, it's just 3, it's just 2, it's just 1. Oh, okay, I'm going to write that. It's x minus 1 to the 1 minus x minus 1 squared over 2 plus x minus 1 cubed over 3 minus x minus 1 to the 4th over 4 plus, so now it's easy to get a general term, isn't it? What is it? Sigma what? Let's use n for a change. N equals, what do you think? 1 to infinity of what? X minus 1 to the n over n. And don't forget the plus, the minus, the plus, the minus. So negative 1 to the n plus 1, isn't it? It has to start positive, right? That would start positive. We plug in 1, you get a square here. That's it. There's your general term. If you can get the general term, you can do the ratio test for absolute convergence of power series. So let's find out the interval convergence of this creature. All right. Are we getting good at this or what? I thought this was tough. Are you okay, guys? Ask me questions. Stop me. Slow me down. Am I going too fast? Oh, goody. What? The only condition is that the function is equal to that series if you add up infinitely many terms and only on the interval convergence. You got to find out what that is. Right? So you don't know what the domain is yet. The domain is the interval convergence. Where does this work, right? So let's find the interval convergence. We've got to do the ratio test. All right, so here's your general term. Let's do the ratio test. How do you write it? The limit as n goes wild, right? Of the what? Absolute value of u sub n plus 1 divided by u sub n. Here's u sub n, so how do you write u sub n plus 1? X minus 1, whoops. X minus 1, what? To the n plus 1 over n plus 1 times, instead of dividing by u sub k, we're right, n over x minus 1 to the n. And this row is only good when it's less than 1. So let's solve for x. Find out when it is less than 1. All right, well, x, well, because remember when we did ratio test, sometimes row could be 1, less than 1, or more than 1. More than 1 was bad, equal to 1 was inconclusive, and less than 1 was convergent. So we're forcing it to converge, right? All right, so what's x minus 1 to the n into x minus 1 to the n plus 1? X minus 1 in the numerator. Can't talk. Numerator. All right. Times this. Okay. So let's do the limit. What's that limit? This is 1. So you get x minus 1 in absolute value is less than 1. What does that tell you about x minus 1? It's between negative 1 and 1. So what does that tell you about x? It's between 0 and 2. So what's the center of the radius of convergence? It's 1. It's the a value, right? This is centered at a. It's either good at a, near a, or everywhere. So it's near a. What's the radius of convergence? 1. Okay, what about the endpoints? Let's see if it works at 0. Let's see if it works at 2. I don't know. The ratio test doesn't tell me. Okay, so, whoops. So here is the function supposedly. All right, let's write that down somewhere. Let's go to the next page. What was it? Negative 1 to the n plus 1. Negative 1 to the n plus 1 times x plus 1 to the n over n plus 1 over n. Sigma n starts at 1. This is the ln of x near 1. But I don't know exactly what near 1 yet, right? It's between 0 and 2, maybe 0, maybe 2. Okay, case 1. What's f of 0? Well, plug in 0. 0 plus 1? 1. 1 to the anything is 1, right? So it's just 1 times this. I get negative 1 to the n plus 1. Oh, is that? I'm sorry. You're right. X minus 1. Sorry, plug in 0. And now you get worse stuff. Sorry. Okay, so it's sigma n equals 1 to infinity of negative 1 to the n plus 1 times another negative 1 to the n, right? Okay, how do you multiply two powers with the same base? I plugged in 0 for x, so it's really negative 1 to the n. Right, 0 minus 1 is negative 1. So is this negative 1 to the what? And remember, 2n plus 1 is always even or odd. Always odd. So if you take a negative number and you have an odd power always, it's going to always be negative 1. So who is this? You know this person. It's this now. Yeah, it's a p series of p is 1, right? It's the opposite of a harmonic dropping the first term. So this is divergent. This at 0 it diverges. What about at 2, the other endpoint? What's f of 2? See, this is why we did what we did last week. This is a series of constants, right? That's what the endpoint is, or anywhere where you plug in x, right? Now let's try the other endpoint. Plug in 2. All right, so it's sigma n equals 1 to infinity of negative 1 to the n plus 1. Then what happens? 2 minus 1 is 1. 1 to the n is 1. So 1 times that is that over n. You know this creature too. Who is this? the alternating harmonic converges. Well, it's not the because I dropped off the first term, but it's damn close. Okay. All right, so then I'm going to amend my interval convergence. Is that correct? Nope, you're missing 1 point. Might as well be complete. Equal to where? At the 2. That's a complete interval convergence. Or if you like, this kind of notation. Right? Same thing? All right, so it's good at 2, huh? Interesting. Yes? Say again, what? Yeah, the domain of Ln is 0 to infinity, but the domain of the power series may not be. All right, the domain of the power series is just, it could be the domain of the function, but it doesn't have to be. It could be less. That's why we're testing. Otherwise, we wouldn't have to test, would we? We would say, oh, yeah, it's just the domain of Ln, 0 to infinity, I'm done. Well, not including 0, and not including infinity. Okay, so there you go. Let's see. So guess what? What did you just prove? You just proved something. You just proved that, where is it? We know the ln of 2 as a series. The ln of 2 is, in fact, this series. And this series, we added it up somewhere along the line. In other words, the harmonic series, right? The harmonic starts at 1. I take that back. The harmonic starts at 1. You can't plug in 0. I don't know what I was saying. And the alternating harmonic and the harmonic start at 1. So this is the harmonic, right? Okay. Didn't we say way back when that the alternating harmonic converged to ln of 2? Yeah. At least we thought it did. We weren't sure. We did a convergence table. We got close to 0.693, which is ln of 2. All right, now we proved it. F of 2 is the alternating harmonic. F of 2 is ln of 2. If you plug in 2, you got ln of 2. You plug in 2, you got the alternating harmonic. So the alternating harmonic converges to ln of 2 exactly. Forget convergence tables. We proved it exact. Okay? That's a big result. It's very hard to figure out exactly what something converges to. That's very rare unless you're a geometric series. Okay? So you got 2 things for the price of 1 here, okay? You've got the fact that the alternating harmonic adds up to ln of 2, and you've got a power series for ln, which is good on this interval. That's a new series you should know. It comes up a lot. We're going to use it. Hang on. We're going to use it. The point of all right, what is the use of this? Power series is just a bunch of powers, x squared, x cubed, x fourth, right? Aren't those easy to integrate or differentiate if you want to? What if you have a function that's really hard to integrate? Change it to a power series and integrate that. That's what we're going to use it for. But remember, it's only valid if you have infinitely many terms, and you can't integrate infinitely many terms on paper, can you? So we're going to truncate it. So next topic, how good is a truncated Taylor series? What's the error term? And how to use it. Why do you use it? Integrating stuff. You know, that's exactly what we're going to do next. So you're right. That's a good question. All right. So any problems? Any questions? Any comments? Anyone? All righty. That's all she wrote. See you later, alligator.